desert wind was howling at 30 miles an hour, whipping red dust across the ridge, but the bumblebee didn't care. Carrying nearly its own body weight in pollen, it flew in a perfectly straight line back to its hive. No deviation, no correction for the powerful crosswind that should have pushed it far off course. Researchers tracking the flight were puzzled. For an insect weighing only a few grams, this level of control was extraordinary, because according to traditional aerodynamic models, the bumblebee shouldn't be able to fly at all. Its wings are too small, its body too heavy, its wing beat too slow to generate the required lift, and yet it flies, not only sustaining flight, but carrying heavy loads, maintaining high speeds, and holding precise trajectories, even in difficult conditions. This is not just an oddity, it highlights a gap between theoretical models and observed reality. The model that didn't fit. The idea that bees shouldn't be able to fly dates back to early aerodynamic calculations in the 20th century. Engineers applied fixed-wing equations to a system that clearly wasn't fixed. The results suggested flight should be impossible. Later explanations introduced the concept of leading-edge vortices, small spinning currents of air generated by rapid wing motion. These help explain how lift is produced, but they don't fully account for everything we observe. They don't explain the bee's ability to fly in straight lines through strong crosswinds or carry significant loads with such stability. Something else appears to be at work. The BBC radar experiment. In a BBC wildlife study, researchers fitted bumblebees with tiny transmitters and tracked their movement using radar. What they observed was striking. Bees didn't simply forage randomly. They often bypassed closer food sources in favour of more distant ones, suggesting decision-making beyond simple instinct. More remarkably, their return flights were almost perfectly straight. Even in winds reaching 30 miles per hour, the bees maintained direct, uninterrupted paths back to the hive. No drift, no visible correction. For such a small organism, this level of stability is difficult to explain using conventional aerodynamics alone. A different perspective. Resonance. One possible explanation lies not in force, but in frequency. When a bumblebee flies, its wings don't simply flap, they vibrate at high frequency. This vibration interacts with the structure of its body, particularly the hollow cavities within it. In physics, when a structure vibrates at the same frequency as its environment, resonance occurs, energy is transferred more efficiently, and systems can behave in unexpected ways. If the bee's internal structures are tuned to resonate with environmental frequencies, it may help explain its unusual stability. Rather than resisting the air around it, the bee may be interacting with it in a more coordinated way. Microstructures and materials. The key to this may lie in chitin, the material that forms the exoskeleton of insects. Chitin is not just structural. At the microscopic level, it forms highly ordered, repeating patterns. These can behave like natural photonic crystals, interacting with light and potentially with other forms of energy. In some insects, these structures include tiny cavities and layered geometries that respond to vibration. When energy passes through such systems, it can be organized, amplified, or redirected. This raises an important question. Could these structures contribute not just to strength, but to flight dynamics? The scarab connection. The same principles appear in other insects. Scarab beetles, for example, possess highly structured chitin layers that scatter light with remarkable efficiency, producing their distinctive bright appearance. Ancient cultures, particularly in Egypt, depicted these beetles with unusual emphasis, often with wings extended in symbolic positions. While typically interpreted as mythology, these representations may also reflect careful observation of natural phenomena. Grebennikov's observations. In the late 20th century, Russian entomologist Viktor Grebennikov studied insect microstructures in detail. He reported unusual effects when examining certain chitin formations, including sensations of heat and pressure, and in some cases unexpected physical interactions between structured surfaces. He proposed that the geometric arrangement of these microscopic cavities could produce measurable effects when combined. His claims remain controversial and unverified in mainstream science. However, the structures themselves, the repeating cavities, the ordered geometry, are real and well documented. Rethinking flight. Taken together, these observations suggest that insect flight may involve more than simple mechanical lift. It may also involve interaction with structure, vibration, and environment in ways we don't yet fully understand. The bumblebee does not appear to struggle against the wind. Instead, it moves through it with consistency and control that suggests a more efficient relationship with its surroundings. Conclusion: the bee's flight challenges our assumptions. It reminds us that models are only as good as the questions they ask. Nature is not limited by our equations, and sometimes the smallest creatures reveal the largest gaps in our understanding.